finally we are going to start the exercises on commutative algebra. I will do the even numbered ones and the odd numbered ones are left to you, like what we normally do. So that means we are starting with number 2. Let's see. Let A be a ring and let AX be the ring of polynomials in an indeterminate X with coefficients in A, or to put it more simply, AX is the usual stuff. It has polynomials which look like this and where the coefficients are coming from the ring A. These AIs are coming from A. In AX we consider such a polynomial f, a0 plus a1x plus a2x squared and so on plus anx to the power n, where n is some non-negative integer. We already know these things. Prove this. Actually there are 3 other parts to this exercise. Today however we are only going to prove part 1, which is a double implication. We have to prove that such an element f is a unit in the ring AX if and only if a0, this coefficient, is a unit in A and the other coefficients a1, a2 all the way up to an are nilpotent elements in A. We start the solution by not directly going for this statement itself, but by proving something else. Let us consider a non-zero ring B. That means B of course is our ring. It's not a general ring, it is still a commutative ring with identity element, and B is non-zero. In B we have taken a nilpotent element A. Let A be a nilpotent element in B. Then by the definition of a nilpotent element, some power of A will be equal to 0 where the exponent is some positive integer n. Alright. I will tell you what we are going to do here. What is it that we are trying to prove here? I will tell you and it will become clear. Now let us consider the case where n is 1. Being a positive integer, n can be 1. That is one of the infinitely many possible cases. When n is 1, a to the power n is of course a. So you get a equal to 0. And that is why in this specific case, if you consider the element 1 plus a, then it is just 1 because a is 0, which is a unit in B. So what we have shown is that for the nilpotent element a, 1 plus a is a unit in B. In this case, if the exponent is equal to 1. But actually it is also true even when the exponent is greater than 1. So that's the next thing we are going to show. So next we consider the case where n is greater than 1. Our exponent has the least value 2 now. I am not saying that it will be 2, but that's the smallest possible value for n now. Now you consider this product, 1 plus a times this sum, 1 minus a plus a squared minus a cube and so on up to this minus 1 to the power n minus 1. Seeing what the sign pattern is, you quickly realize that this should be n minus 1 if it has to come with a to the power n minus 1. And till that only we write. Now if you do the multiplication and see what you are getting, there will be many terms which will cancel each other, and ultimately you will be left with this 1 minus a to the power n, but a to the power n is 0, so you are getting 1. Do you see what you have got here? 1 plus a times some ring element. This is after all in its entirety a ring element in our ring B is equal to 1. So by the definition of a unit in a ring, 1 plus a again is a unit in this case also. That means if you take a general nilpotent element in a ring and add the identity element 1 to it, then that sum becomes a unit in the ring B. Next, what we do, we use this freshly proven fact that the identity element plus a nilpotent element is a unit to extend this itself. This time we are choosing any unit u in the ring B. U is any unit, just like this identity element is a special element, but after all it's also a unit. This time we are taking any unit u in B. Because u is a unit, so its multiplicative inverse, u inverse exists in the ring, and that is why we can consider the product of u inverse and our original nilpotent element A. Okay. We are saying that this is also nilpotent. Why? You consider its nth power. Because we are in a commutative ring, that nth power will be equal to u to the power minus 1, or probably that's not how I should say, u inverse to the power n times a to the power n. That will be equal to the nth power of u inverse A. But a to the power n is 0, so that's how the nth power of this element is also equal to 0, and that is why this is also nilpotent. So by what we proved just now, if you then add the identity element to this nilpotent element, again you are going to get a unit. Alright. Hence, now you have considered the sum of u and A. You can write the sum as this product, u times 1 plus u inverse A. If you do the multiplication, you will have u times 1, that means u, plus u times u inverse A, that means A. And that is also a unit. Why? Because u originally is the unit, and we found out that this is also a unit, and we know that in a ring, if you take the product of two units, then that product is also a unit. That is why. So we have uncovered this fact, that is, the sum of a unit and a nilpotent element is again a unit in any ring, the type of rings we are considering, commutative ring with identity element. We are now going to use this fact to prove our main thing. Let us start the proof with this condition, that is, A0 is a unit and these other AIs, where I varies from 1 through n, are nilpotent elements in the ring A. What is it that we have to prove? We have to prove that that polynomial f, which is A0 plus A1x plus so on up to ANX to the power n, that then is a unit in the polynomial ring AX. Okay. Now because A0 is a unit in the ring A, it is also automatically a unit in AX. Why? What does it mean for A0 to be a unit in the ring A? It means that there is an element, say C in A, such that A0 C is equal to what? The identity element. But you can think of A0 and C as elements in the larger polynomial ring also, which contains A as a subring. So this equation A0 times C is equal to 1 is also an equation here, and that tells us that A0, just like it's a unit in A, it's actually also a unit in AX. And what about these other AIs? These are given to be nilpotent elements. Where? Nilpotent elements in the ring A. And that's why we are saying that these polynomials, a1x, a2x squared, all the way up to anx to the power n, are nilpotent elements in the polynomial ring AX. How? Let us just arbitrarily take any one of these, say a2x squared. It is given that a2 is a nilpotent element. So that means some power of a2, where the exponent is a positive integer, is equal to 0. Say a2 to the power m, m is equal to 0, where m is the positive integer. Now you consider the nth power of a2x squared. Obviously that will be equal to a2 to the power m times x to the power 2m. But a2 to the power m is 0, So that's why you get the 0 element of this ring, and hence this is also nilpotent. Similarly, these other polynomials, all of them are nilpotent. Alright. So now what do we have with that? So by the above paragraph, means the one where we proved that the sum of a unit and a nilpotent element is a unit, by that result in fact our polynomial is a unit in Ax. But how? How are we suddenly concluding this, which we want? You look at, I have intentionally written this as well. You can just simply write a naught and then plus dot 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 plus a n x to the power n. But to see what is going on and how this conclusion can be drawn from what we did here, we have these first 3 elements. So what did we say here? A naught is a unit in Ax and A1x is a nilpotent element in Ax. And we have just now proved that a sum where one summand is a unit and the other one is a nilpotent element is a unit. So A naught plus A1x, this much is a unit in Ax. But because that is a unit in Ax and A2x squared is nilpotent, so again this slightly larger sum is a unit, and it goes like that till you reach this, and the final conclusion is that the entire thing is a unit in Ax. So you have proved one of the 2 implications. Now we will prove the reverse implication. Conversely, let f be a unit in Ax. We have to prove that A naught is a unit in A and the other coefficients A1, A2 up to An, they are nilpotent elements in A. Now because f is a unit in A, there exists a polynomial g in Ax, of course, say b naught plus b1x and so on up to bmx to the power n, such that fg is equal to 1. Now from this equation we are going to get many conditions, because fg means you will multiply these 2 polynomials, that one and this one, and then you do your usual calculation, and finally fg will come as a polynomial itself. I mean it is, but you have to rearrange things. You already know what you have to do. You gather the like terms, add their coefficients, that stuff, and then you have to equate that polynomial to the constant polynomial 1. So the constant part of the product polynomial fg will be equal to 1 and the other coefficients will be equal to 0. So let us write the conditions. So these are the conditions. Conditions means equations. A naught b naught is equal to 1. So A naught b naught is actually the constant part of the product polynomial fg, which is really easy to see. And then this is actually the coefficient of x, that should be equal to 0, because on this side it is 0. On this side means here. A1 b naught plus A naught b1, and like that it goes. You know there will be other intermediate coefficients, all of them will be equal to 0, and eventually you reach this an minus 2 bm plus an minus 1 bm minus 1 plus an bm minus 2 equal to 0. Then the next one, an minus 1 bm plus an bm minus 1 is equal to 0, and finally the product of the leading terms of both the polynomials. The leading term here for g is bm and the one for f is an, and this is actually the coefficient of x to the power n plus n, that is also equal to 0. And now you have to somehow from these equations figure out that A naught is a unit and the other ai's are nilpotent. The first part is already, you can see that from the first equation itself, because A naught b naught is equal to 1, A naught is a unit. But what about the other ones? How do we show that the other ai's are nilpotent? So we write our first conclusion from this equation that A naught is a unit. And now you look at this calculation. A n squared bn minus 1. In its place we have written an times an minus 1 bm plus an times bm minus 1. How? Well, you see from this one, if you do the multiplication, what will you get? With an minus 1 you will get an bm, but an bm is 0, so this term will vanish, plus an square bm minus 1. So that means this step is clear, but this is 0. an minus 1 bm plus an bm minus 1, and that is why the product is 0. So we have got something, an square times bm minus 1 is equal to 0, but it doesn't stop here. Now we will do more calculations like this. The next such element to be considered is this, an cube times bm minus 2 this time, and in its place we have written this, an squared times an minus 2 bm plus an minus 1 bm minus 1 plus an bm minus 2, which you can see is the left hand side of this equation. That's why I kept this part, I did not erase it. But how is this true? You do the multiplication, what will you get in the first term? Besides other things, you are getting an bm. There is another an also, because an squared, and you also have an minus 2, but you have an bm which is 0. So that means this term actually is not there, plus an squared times an minus 1 bm minus 1. But you have just now proved that an squared times bm minus 1 is 0. So this term also vanishes. And what do you get from multiplying this to an cube bm minus 2? Alright. But this thing is just this thing which is 0. So that's why this is also 0. And we then next write, continuing like this, continuing the calculations in this pattern, we eventually get this, an to the power n plus 1 b naught is equal to 0. How? Does it follow the pattern? Let us see. When you have 2 here as exponent, then you are subtracting 1 from m. You are subtracting 1 less than the exponent from m here. That's how you got m minus 1. Here also the exponent is 3, but you are subtracting 2. So if the exponent is m plus 1, then you will subtract 1 less than m plus 1, that means m, from what? From m minus n. That's why you have 0. That is equal to 0. This is not a this is not a complicated thing to understand, but what is a little complicated and I think a little confusing also is convincing yourself that you can continue in this pattern, the calculation. For that, you will have to really write enough number of equations that we wrote there, using which we are doing all these things. So that part I am leaving to you. You write not just a naught b naught is equal to 1 and the other equations, but many equations in between. And then you go through not just this and this, you can see this too already, but say 3 or 4 or even 5 such calculations which will naturally come after this. Then you will see the pattern and then you will convince yourself that yes, it can be continued. So we have now got this. Now how can we use this? So next you consider only this power of an without b naught, an to the power m plus 1. In its place, of course, you can write an to the power m plus 1 times 1, the identity element. But you recall our first equation, 1 is equal to a naught b naught, or you can write as b naught a naught because our rings are commutative. But just now you have seen that this times b naught is 0, so that is why this is also equal to 0. Now we are finally somewhere. that is useful to us. We have proved that a power of an, where of course m plus 1 is a positive integer, is equal to 0. So an is a nilpotent element in A. We have proved that at least that the leading coefficient of our polynomial f, which is an, is nilpotent. But that suddenly scares you. What about the other coefficients, an minus 1, an minus 2? Do we have to go through such calculations for each one of them? Luckily, no, we do not have to do any more such calculations. From this itself, we can milk it again and again. We will now see how. So we next move on from this conclusion that an is nilpotent in A. Because of that, an x to the power n is a nilpotent element in the polynomial ring Ax. We have already seen this. But then f minus anx to the power n is a unit in Ax. Again we are using our result that we proved in the first paragraph, that the sum of a unit and a nilpotent element is a unit. I mean, you do not actually see sum here, you see difference, but you can think of it as the sum of a and minus anx to the power n. That is also nilpotent. So now you have got, previously you had f, which was a unit. Now you have got this other polynomial which is a unit in Ax, and that polynomial is this. The leading term from f has been removed. So what did you prove just now? That if a polynomial is unit, then its leading term is a nilpotent element. This is a unit now, and it's a polynomial, and its leading term is an minus 1. So similarly, an minus 1 is also nilpotent in A. And now you can clearly see that you can continue this as long as, until all the coefficients are exhausted. Because the pattern is now clear, we just simply write similarly the other coefficients. I have written them in this order, not starting from a1, because that's how things are going. First we said that an is nilpotent, then an minus 1. That's why the next one is an minus 2, an minus 3, all the way up to a1. These are also nilpotent, and that completes the proof.